Okay, tonight I'm talking about global and regional sea level change, what's happened, why is it happening, and what are the future implications. I come from the Climate Change Centre at the University of New South Wales. So tonight I'm going to give you an overview of sea level science, start off with why it's an important issue, a little bit about historical sea level change, understanding 20th and 21st century sea level change, projections for the 21st century, and the longer term implications, and finishing off with some conclusions. So we live in a coastal society. This is just one example of a city, the Gold Coast, which has gone from a very sparse population to quite a substantial population over a period of about 40 years. And there's many locations around the world like this. So ours is a coastal society, it's a growing coastal society, and many of our coastal cities were built in a period where local sea level has been falling. So we could build right up to the coast. If we actually look at the numbers, then the numbers are large. So these are the numbers of people living in the low elevation coastal zone. That's a zone up to about 10 metres above current sea level. 2.3% of the area of the globe, but about 11% of the population. At very high, up to very high population densities, 241 people per square kilometres. Most of these are in developing nations, particularly in South and East Asia. So if you look at the numbers, so 2000, the numbers are about approaching 500 million people living in this zone, and over the next 50 years, that increases up to over $1 billion. These numbers are probably fairly rubbery, but whatever way you think about it, they are large numbers of people going to be affected by sea level rise. So a slight update on that. In 2010, there were 230 million people living within 1 metre of current sea level. And we're talking about a sea level rise during the 21st century up to about a metre. 400 million within 2 metres, 700 million within 5 metres, and over 1 billion within 10 metres. So once again, these numbers are very large. So what's happened historically with sea level? This shows a record of sea level over the last 550,000 years, from the most recent on your left up until 550,000 on the right. And the scale here is 0 to about 120 metres. So sea level was much lower in glacial times, typically over 100 metres lower than current day sea levels. And it's oscillated between roughly current day sea levels and these lower values on about 100,000 year time frame. If you now fast forward and look at just the last 20 or 30,000 years, sea level in the last glacial maximum, which is about 20,000 years ago, was over 100 metres below present values, probably more than 130 metres below present day values. And then it rose rapidly through this period here at average rates of over a metre per 100 years for many thousands of years, and with peak rates of 4 metres per century, or over 4 metres per century. So we know that sea level was lower during cool periods, but perhaps more important to us now is what happened to sea level during warm periods. And shown here is estimates of sea level for the current day. So carbon dioxide concentrations have increased from about 280 parts per million. When this diagram was drawn, there were about 2014, they're over 2020 parts per million now. And in that time, temperature has risen by about 1.2 degrees Celsius up to today. If you go back to the last warm period, the last interglacial period, so it's about 130,000 years ago, sea levels were somewhere between 5 and 10 meters higher than current values, shown here as 6 to 9 meters. At carbon dioxide concentrations roughly equivalent to pre-industrial levels, so 280 parts per million, and temperatures somewhat similar to today's. You go back to 400,000 years ago, you get a somewhat larger rise, 6 to 13 meters, somewhat warmer temperatures, but still at carbon dioxide concentrations similar to today. If you go back to 3.3 million years ago in the mid-Pliocene warm period, then sea levels were substantially higher, anywhere between 6 and, what do they say here? So 6 to 20 meters and possibly more above current values. At CO2 concentrations, which were substantially larger than pre-industrial, but somewhat similar today. So what this record is telling us is not only were sea levels much lower during cold periods, they were also substantially higher, meters higher, during past warm periods. And what it turns out, of course, the oceans and the ice sheets have long time frames, so the current sea level is out of balance with the current and the evolving climate. So what causes sea level to change? Depicted here is the main components of that. Firstly, as you warm the oceans, water expands, and just like a thermometer, sea level rises. And that's one of the principal components for 20th and 21st century sea level rise. You also have loss of mass from glaciers around the world, glaciers like Patagonia, Himalayas, Alaska, etc. And that water runs off into the ocean, changing sea levels. You also can have changes in mass with the ice sheets. Ice sheets are somewhat more complicated. So for Antarctica, you can have more increased precipitation on Antarctica, which tends to lower sea level on its own. But you also have a more rapid flow of ice into the ocean, rising sea levels. And this is one of the really big uncertainties. What that focuses on is really what's the volume of water in the ocean. But what we're interested in, of course, is sea level relative to the land. That's what impacts, and that's called relative sea level. And that's what coastal tide gauges measure. Satellite altimeters also measure sea level, but they measure sea level relative to the center of the Earth. And so we need to be careful about what reference frame we're working in when we try and understand this. Three other components of sea level change. We've been building dams during the 20th century and storing substantial amount of water in these dams. And we've also been mining water from aquifers and depleting aquifers, and this water eventually flows off into the ocean, counteracting much of the storage of water in dams. And finally, there's also natural changes in the water stored on land through the drought flood cycles affecting parts of the world. So for example, in 2010, 2011, sea level globally fell by about 5 millimeters as there was major flooding in Australia and Pakistan and a couple of other places. And the importance about Australia in that context is there's a very long time for that water to make its way back to the ocean because there's inland seas. So how do we measure sea level? So the traditional way is with coastal tide gauges, as shown in the top panel here. So you measure sea level relative to the wharf, And if you also know how the land is moving by using GPS facilities, you can get sea level in an absolute sense. But these days we also, so before I go on, the tide gauges only give you local sea level, and they're scattered around the world. They start in about 1770 as one of the earliest records, and they've gradually increased since then. Since 1993, we also measure sea level with satellite altimeters. So these are satellites which send a radar pulse down to the ocean floor, ocean surface. It bounces off the ocean surface back to the satellite. You measure the time of flight, and you can work out what the distance between the satellite and the sea surface is. And if you independently measure where the satellite is by various techniques, laser tracking, GPS techniques is probably most used these days, you can work out what sea level is relative to the center of the Earth. So a program that John Gould has been heavily involved in is the Argo program. There's a program of floating floats, so these yellow floats in the bottom picture here, which are thrown into the ocean. They sink down to 2,000 meters, drift, come up to the surface, measuring the temperature profile and the salinity profile as they come, and sending that data back via satellite. So this gives us, for the first time, really essentially global coverage of the upper 2,000 meters of the ocean, and people are working on extending that to the ocean floor. People also measure deep ocean temperatures from ships, research ships, making measurements directly from those research ships. And now we can also measure the mass of the ocean from what's called the GRACE mission. So this is a gravity mission. So you actually have two satellites here on the lower right-hand corner. They measure the distance between the satellites, and then as the satellite orbits the Earth, it goes through a changing gravity field, and so the satellites can either get closer together or further apart, and you can use that information to infer the gravity field. And we're particularly interested in how that gravity field is changing, and that is in response to changes in the distribution of water in the ocean and also on the land. So this, for the first time, gives us essentially a complete suite of measurements, measuring the ocean mass, changing sea level, measuring the ocean volume by its changes in temperature, and measuring sea level directly by satellites or coastal measurements. So the global climate programs, starting in the 1990s, late 1980s, have really revolutionized our understanding of sea level and of the climate system. So again, John Gould's been involved in leading the World Ocean Circulation Experiment and the CLIVA program, and also the revolution in observational techniques with satellites, the Argo program, the GRACE program, have really changed our perspective of our understanding of the oceans and sea level change. Shown here is the rate of sea level rise from 1993 up to about 2023. So the red areas, so sea level's rising virtually everywhere, a maximum of about 6 or 8 millimeters per year in the Western Pacific, and closer to just a couple of millimeters per year in the Eastern Pacific. This pattern is primarily a result of natural variability, the ENSO cycle of the Pacific, and longer period oscillations of the climate system. But the pattern of change has also allowed us to reconstruct sea level using coastal tide gauges. So the altimeter gives us a global picture, and you get these type of maps every 10 days, but the tide gauges go back much longer in time. So we can combine the information from the spatial distribution we get from satellites with the time series from diode gauges to construct global mean sea level and its regional distribution. And what's shown here is a whole series of different estimates of global mean sea level by different groups. So I did one of the very early studies and that's shown in the orange. Don't know whether you can see that. So that's through here somewhere. And we've just been updating that in a new study shown in green. And if you take out the one or two outliers here, particularly this outlier, the blue one here, which is essentially coastal sea level rather than global mean sea level, then there's actually quite good agreement between these various estimates. So sea level during the 20th century has risen by about 20 centimetres, and it's rising at an accelerating rate. This is a rate of sea level rise over a 30-year period, starting in 1900 to the present. Our two different estimates of the rate of rise during this period, and that's increased from about 1 millimetre per year at the start of the 20th century. It rose to about 2 and then fell down to perhaps 1.5 and is now well over 3 millimetres per year during the 30-year period. And if you actually look at the most recent data, you're about 4 millimetres per year. So quite a large acceleration during the 20th century. And you can look at that a different way. If you plot those rates of rise as histograms, then the average, most observations are in this region of 1 to 2 millimetres per year. And then there's this long tail here, and the modern satellite measurements are shown by the three vertical lines there actually. They're right at the very end of this continuum of rates of rise. So again, an indication that the rate of sea level rise has been increasing from 1900 up to the present. We have an approximate understanding of why that rise has occurred, and shown here is some of the different contributions we can estimate from global thermal expansion, loss of mass from glaciers, loss of mass from ice sheets, and changes in water stored on land. In the red curve, our estimate of global mean sea level just from tide gauges in the blue curve. So over the whole period, there's quite a good agreement, but there's not perfect agreement through the 20th century. And again, if you look at the rates of change, you find in the roughly around 1930 that the sum of contributions that we estimate is larger than the observed rise, and from about 1960 up to the present, the sum of contributions is smaller than the observed rise. So we've got some work to do to fully understand this. This shows a regional, or global and regional sea level budget done by Jinping Wang. So the top right-hand panel, so the sea level reconstructions give you about 2 millimetres per year over this period from 1970 up to the present. The sum of the contributions is about 1.8 millimetres per year, so slightly less. And the major contributions to that are ocean thermal expansion, warming of the ocean and its expansion of water, and secondly, loss of mass from glaciers around the world. There's a smaller contribution from the ice sheets, but a rapidly growing contribution from the ice sheets. So both Antarctica and Greenland have increased several-fold over the last 20 years in their rate of contribution. So this is a really worrying sign for the future. The time series on the top left are all the different contributions from glaciers, ice sheets, terrestrial water storage, and ocean thermal expansion. And then the comparison between the observed and the reconstructed sea level are shown by these curves here. Now each of these signals has a regional distribution. As you change the distribution of mass on the Earth, you change the gravitational field, you change the attraction of the ocean to regions of concentrated mass, and you change the Earth's rotational field. So for example, if you look at this field, this is a fingerprint associated with the changes in mass of the ocean. You'll notice that up here near Greenland, the sea level rise from this contribution is much smaller and perhaps even negative when you get close enough to Greenland. And this is associated with the loss of mass from Greenland, less gravitational attraction, so the water flows away from Greenland, and also the land itself rebounds as you take mass off the surface. A picture of ocean thermal expansion here. So again, it's not uniform over the globe. Glacial isostatic adjustment, GIA. So since the last glacial maximum, there's been very large amounts of water transferred from the land to the ocean. And that has resulted in ongoing movement of the land today, called glacial isostatic adjustment, which means that in many parts of the world, sea level has been falling over the last few thousand years up until the last couple of hundred years. And in the bottom right-hand corner is the sum of all those contributions over this period. So sea level rising virtually everywhere from these contributions. What about projections for the 21st century? This shows the projections for two scenarios. On the bottom, a high mitigation scenario, which ends up with about 2 degrees Celsius of warming by 2100. And so on are three different assessments. The fifth assessment report from the IPCC, which I was essentially responsible for, special report on oceans, climate and cryosphere, and the most recent report, the sixth assessment report. And its rate of its rise is a few centimetres higher than the AR5 over the 21st century. But they're not very different. What's shown in the shading is what's called the likely range. So this is the likely values of that sea level will rise by. But it could rise by more, and we'll come to that shortly. So we've attempted to say, well, how good are these predictions? If we compare the small overlap period we've got from the projections with the observations, how well do they compare? This shows the satellite altimeter record, showing a very clear acceleration from 1993 to the present, an acceleration of about 0.12 millimeters per year. And shown in the next panel is a comparison of the projections with the observations over this period. So what we do is take the observed global mean sea level, fit various climate variables like the ENSO index to that, and also a linear and a quadratic fit. And that's what's shown on the bottom here. So the observed acceleration and then the projected acceleration. If you actually compare trends over the overlap period, they're virtually identical, but you can't differentiate between scenarios over this period. But if you look at the acceleration, you actually find that the acceleration in the higher scenarios is quite a bit larger than in the lower scenarios. And the observations actually appear to be tracking close to the upper level of the projections, not the lower level. So what I showed previously was what's called the likely range, but there are some uncertainties, particularly associated with the two ice sheets, Greenland and Antarctica, particularly West Antarctica. These uncertainties tend to be one-sided, so they could lead to a substantially larger rise than what's in the likely range, but not a substantially smaller rise. And when you look back at the past, that indicates at temperatures even today, sea level should be substantially higher than it is. This is associated with the long timescales of the ocean and the ice sheets, such that current sea levels is out of balance with our current climate forcing. This higher range is quite uncertain, but what they said in the AR5 is they showed this diagram, which went up to about 1.6 meters, but they actually said it could even be larger than this. What's also important here is the rate of rise in 2100. At the lower end of down here for SSB 2.6, which is 2 degrees warming in 2100, or the 1.5 degrees warming in 2100, then the rates of rise are a few millimeters, so they increased during the 20th century and then slightly decreased by 2100. But for the high emission scenarios, the rate of rise continually increases during this period, approaching or exceeding rates of 1 meter per century. So that's the rate that we saw after the last glacial maximum, where we had 1 meter per century for many thousands of years. So that implies that sea level is not going to stop in 2100 in any of these scenarios. It's going to continue to rise and continue to impact society. Well, you might say, well, I'm pretty critical of these models. They're approximate. They've got lots of uncertainties in them. What if we just look at the data itself? And that's what's shown here. For one particular record, we've taken the Sydney record and fitted quadratic and linear and climate variability to that, and it actually quite agrees with the projected scenarios, and again is at the upper limit of the projected scenarios for this particular location. So we're currently working around the globe to do this for many different stations. Projected sea level is not going to be uniform around the globe. So sea level, the ocean surface is not flat. There are ocean currents, and that causes a gradient in sea level. So just think about your weather map that you see each night. Then there are horizontal gradients in the atmospheric pressure, and that's associated with wind patterns. You have exactly the same phenomena in the ocean. You have ocean currents causing gradients in sea level. And that's what's shown on the top here. This is the amount of changes in sea level from ocean thermal expansion and changes in currents. So you have a couple of features here. One is a maximum in sea level at about 30 to 40 south in the southern hemisphere, and a similar maximum in the northern hemisphere. So these are at the extremities, the poleward extremities of what are called the subtropical gyres. And right near Antarctica, you have a minimum in sea level compared to elsewhere, and then there's a more complex pattern in the North Atlantic associated with changes in the ocean overturning circulation. So that's one contribution to changes in regional sea level. The second one is glacial isostatic adjustment. So this is the response of the ongoing response of the Earth since the last glacial maximum to changes in surface loading of the Earth. Changes in glaciers, changes the distribution of water on Earth, changes the gravitational field, changes the deformation of the Earth, and changes the rotational field of the Earth. And similarly for ice sheet mass loss. When you put all of these components together, these are the projections from the AR5. So this is a 2013 report. Virtually everywhere, perhaps with the exception very close to the ice sheets, sea level is rising. So it turns out for much of the ocean, or much of the world's coastline, 80% of the world's coastline is rising at the global mean sea level within about 20%. So global mean sea level is actually a good approximation for local changes. But there are other effects that can also change relative sea level as well. Shown here is an estimate of vertical land motion at 40 of the major coastal cities around the world. So on the left is Ho Chi Minh City, and there the land is sinking. And that's, so you can have various factors, but the dominant factor in coastal estuaries around the world is compaction of sediments just by the weight of the sediments. And then most importantly, if you extract water or petroleum from those sediments, they compress more rapidly. And that's what leads to this excess rise in sea level. So this is something we have perhaps greater control over. We can stop the extraction of groundwater and stop the sinking of these cities. So you probably know Jakarta, the Indonesian government is shifting their capital from Jakarta because they're experiencing increasing flooding levels to somewhere with a more stable sea level. And that regional distribution is quite large. This is a map for Jakarta on the top left-hand corner of the rate of sediment compaction around the city. So up here in the top left, and that corresponds to this blue curve down here, and that's the rate of what is it? Quite a large rate actually, of many millimeters per year. Of course, sea level, the impacts of sea level are going to be felt first through the impact of extreme events. This is just one particular extreme event for Sydney. Swimming pool landed up on the beach, many houses teetering on the edges from coastal erosion. And these extreme events can be caused by tides, storm surges, waves, seasonal to interannual variability, and of course sea level rise. So we need to put all of these things together to understand the impacts of sea level rise on our coastline. And it turns out that there can be a very rapid increase in the frequency or the decrease in return period of extreme events of a given level. So shown here is what's called the multiplication factor for around the globe. So a multiplication factor of 100, so this orange colour, means that what is currently a 1 in 100 year event, by 2100 will be occurring once a year on average. So parts of Europe, it's more like a factor of 10, so the 1 in 100 year event will be occurring roughly once every 10 years. But many other locations around the world, the 1 in 100 year event will be happening several times a year by 2100. So where are we now? This shows a comparison of our observed temperature change with what is projected given our various emission scenarios. So we're aiming at maintaining temperatures at 1.5 or as close to 1.5 as we can. We're already at about 1.2. So we're getting extremely close to this threshold already. If you take governments' policies and actions, so these are actually implemented policies, and say how much mitigation will they achieve, then you're talking about a median estimate of 2.7 degrees Celsius, almost twice the 1.5. If you add to that their 2030 targets, you're down to about 2.4. You talk about promises that they are making, pledges that we will be carbon neutral in 2050, often without any means of getting there, then you're still talking about 2 degrees, and only the most optimistic scenario will you get below 1.8 degrees. And unfortunately, many countries are not living up to their policies and their pledges. So we're going to have to adapt. We cannot stop all sea level rise, even if countries really did fulfill their promises. We will still have to adapt to rising sea levels. And so what are the options available to us? There's three basic options, and we're doing all three of these already. We're abandoning parts of the coastline, shown in the top level, top picture, where they're realigning the coastline, abandoning some of the coastline because it's just too expensive to maintain. We can adapt to rising sea levels, building houses or raising houses above the sea level. So the middle picture on the left is our storm surge shelters in Bangladesh. So Bangladesh has quite severe storm surges, and this has saved many tens, hundreds of thousands of lives in these simple shelters. And of course we can protect parts of the coastline, things like the Thames Barrier, similarly in Rotterdam, and these can either be hard engineering solutions like the Thames Barrier, or more soft engineering such as vegetation on the coastline and sandbars, etc. So what are the ongoing challenges? So accurately estimating ocean heat content. You need to remember that climate change is about the energy balance of the Earth system. About 90% of the energy that's stored in the climate system now is in the ocean. And only about 1% in the atmosphere. We need to understand that energy budget. We need to understand the sensitivity of the climate system to carbon forcing. To do that, we need ongoing observations, coupled ocean atmosphere, cryosphere models, and land surface models. And we need a suite of models for the different scenarios. The Greenland and Antarctic ice sheets are the biggest uncertainties for sea level, particularly the West Antarctic ice sheet. It's potentially unstable. The West Antarctic ice sheet is grounded on ice below sea level, and that bedrock gets deeper as you go back from the coastline. This is a potentially unstable situation. If you have a retreat of the grounding line, then that means there's more flow of ice into the ocean because the ice is now thicker, and that leads to a further retreat of the grounding line. So there's a potential instability of the climate system. So there's a question, have we passed that instability in any region? Well, we don't really know, I think, is the answer to that. There's some suggestions that in parts of West Antarctica we might have at least be approaching that threshold. For Greenland, Greenland is somewhat different and somewhat easier situation because in Antarctica it's too cold for there to be significant melting, so it's a flow of ice into the ocean that's important. For Greenland, it's contribution from both the flow of ice, but a larger component from the surface melting of the ice sheet, and that surface melting increases at a rate more rapidly with temperature than increased snowfall, leading to a decay of the ice sheet. There's suggestions that, we've always talked about there being a threshold for the Greenland ice sheet. We don't know exactly what that threshold is, somewhere between 1 and 3.5 degrees Celsius. Beyond that temperature, surface melting alone, no matter what happens to the flow of ice into the ocean, leads to an ongoing decay of the Greenland ice sheet. Greenland ice sheet contains about 7 meters of sea level equivalent. West Antarctica about 5 meters sea level equivalent, and the total Antarctic ice sheet about 58 meters of sea level equivalent. We need to robustly attribute the observed changes we're seeing to the forcing, greenhouse gases, aerosols, etc. We need a much more thorough study on extreme events and how they're changing and what we can do about those. So climate variability, surface waves are also important because that's actually the medium by which a lot of the damage is done. Support for mitigation of impacts. We cannot stop all sea level rise, as I said, so we're going to have to live with it, learn to adapt to it. And communication of the results is really important. So there are legal implications. So I've been involved in court cases associated with coal mining and sea level. It has policy implications for government and, of course, public planning for cities around the world. So in summary, our society, today's society, is a coastal society, and we're potentially vulnerable to the impacts of rising sea levels. In a warmer climate, sea level is higher and meters higher than current values, and remembering that very large population densities in those coastal regions. Sea levels are rising at an accelerating rate, and they have been rising at an accelerating rate during the 20th century. Current understanding is that models, ocean thermal expansion and glaciers are the two largest contributions to the 20th century, but ice sheets have significant uncertainties and are a growing contribution. Avoiding crossing thresholds really means urgent, significant and sustained mitigation of our emissions. Without that, we will be impacting the lives of many hundreds of thousands or many millions of people during the 21st century and beyond. Mitigation can reduce the impacts but can't stop it. Sea level will be felt first through the extreme events, and there is ongoing need to reduce uncertainty. And I just repeat that sea level is not going to stop into 2100 under any scenario, but we can affect the rate of rise after 2100. So, thank you.